Find the invariant lines of the transformation given by the matrix 3, 1, 2, 4. Okay, so basically what we're trying to find here is lines that do not move under this transformation. This is opposed to invariant line of points, where the actual points themselves don't actually move under the transformation. So the point can actually move on the line in this case. It doesn't actually have to stay in the same place, but the only thing it must do must be on the line. Okay, so how do we go about doing this? Okay, so the invariant lines will be of the format of a straight line, which is y is equal to mx plus c. So any point under this transformation will become x dash y dashed, 3, 1, 2, 4, and then any point x, y. When we multiply out the matrix, it's 3 times x plus y, and then 2 times x plus 4y. The thing is that it must be equal to mx plus c, so we'll replace y with mx plus c, so we get 3x plus mx plus c, and then 2x plus 4 times mx plus c. Simplifying, we just get 3x plus mx plus c for the x dash value, and we get 2x plus 4, multiplying the bracket out, 4mx plus 4c. Now this point must be on the line of y dashed is equal to mx dash plus c. So my y coordinate, 2x plus 4mx plus 4y, must be equal to m times my x coordinate, which is 3x plus mx plus c, and then we also have to add c to that. So writing that out again. If we now expand that bracket, so we get 2x plus 4m plus 4mx plus 4c, then we get 3mx plus m squared x plus mc, or cm, plus c. Okay, so bringing the thing over here, making this equal to 0. So we're going to have m squared x. Bringing 4mx over here will make it minus mx, sorry, and then bring the 2x over will make it minus 2x. And then bringing the c over here, we're going to get cm minus 3c, 4c. C minus 4c will give me minus 3c. Okay, we've got a common factor here of x in this first part, so we're just going to have m squared minus m minus 2x, and a common factor c here, so we're going to have m minus 3 times c. Right, so if this is going to be equal to 0, that means that both this or this or this must be equal to 0. So that's going to give m plus 1, m minus 2 is equal to 0 when we factorize this. Here we can either say that will give m is minus 1, m is equal to 2, and that m minus 3 is equal to 0, or c is equal to 0, which will give m is 3, or c is equal to 0. But this cannot be a solution, because if I put that in here, it won't be equal to 0. So c must actually be equal to 0 for this statement to be true. So no, m cannot be equal to 3, for m is equal to 3. M squared minus m minus 2 is not equal to 0. C must be equal to 0. Hence, m is equal to minus 1, c is equal to 0 is one possible solution, which gives the line y is equal to minus x, or m is equal to 2 and c is equal to 0, which gives the line y is equal to 2x. So the invariant lines under the transformation m are y is equal to minus x, or y is equal to 2x. Now we can look at this using this GeoGebra app. Okay, so here we have our given matrix, which is 3, 1, 2, 4. We can see the two invariant lines here. So for example, we can see here that b moves here, but it's on the same line, and that d moves down here, but it's actually on the same line, 2x. And similarly on this one here, we can see that c moves to c dashed, and that a moves to a dashed. Okay, so this GeoGebra app I will put in the notes of the video. there's a screenshot of what I've just explained. There's a whole solution here for you as well. I hope you've understood, and I thank you very much for watching. In the next video, I'll look at one where c is not equal to 0.